So, good evening, everyone. Today is the third live session of the Transport Phenomena in Biological Systems class. So, today we'll be solving problems and we'll be going through the derivation because this derivation is a little bit tough. And if you practice it more, you will be it will be easier to remember. But derivations are very easy if you do it systematically, right? So, whatever sir has done, we will do it. We will not do all because of the time constraint. If you have any particular question regarding particular derivation or problems, so you can definitely tell. Otherwise, I will do the most important parts of this week, most important derivations of this week, and then I will switch to the question answer session. We'll do some derivation there and some problems, numerical problems. Okay, so let's start today's session. I'm sharing the screen. I hope it will be visible. I think my screen is visible, right? Yeah. Let's start. So in this week, sir did some derivations, right? So 4 or 5 derivations, important derivations sir has done. So first one is about the steady state diffusion. Steady state diffusion in or across tubular walls. Across tubular walls, right? Second one is and this is done in a tubular means tube form. So it will be easier to do in cylindrical format. Cylindrical coordinate. Second one is about steady state radial diffusion in spherical pellet, right? Third one, steady state radial diffusion in with reaction. Steady state radial diffusion with reaction. Fourth one is unsteady state diffusion, and fifth one is pseudo steady state approximation. Right? So all these 5 derivations, if you practice with yourself, So it will be very important because these types of questions may come. But in today's lecture, I will show the option 3, that is the steady state radial diffusion with reaction, where you will be getting to know about the Thiel modulus effectiveness factor, because this is the most important part of this lecture. And second one, if time permits, at the end, I will try to do the unsteady state diffusion. All derivation steps, everything is already given in the source notes. If you can do it yourself also, I will be doing, because this is little bit tough. That's why I am repeating this. Okay, so let's start that. So when it is told that it is spherical coordinate, right? So that means spherical radial coordinate equation we need to write. So Navier-Stokes spherical coordinate equations, right? So exact equations you can follow, but I'm just showing it from here. So that this is a huge equation, so it is little bit difficult to remember, but you write it on your own, because these equations will be always given. They will not ask you to write the equation, right? Where is it? So you remember the equation. If you remember the equation, you can directly write it from there. Or else you can find it here. What 2D fluid? Okay. Yeah, this is cylindrical coordinate, and this comes the spherical coordinate. Simplified version is not given. Yeah, and this one also, it is little bit complicated showing. Then it will come on that. Anyway, you can, if you have, I think from the class itself, you have noted it down by yourself. It will be not very difficult to find it. Also, it is there in any continuity equation or moment transport phenomena books, right? The book I have told, Bartlett-Stewart equation, right? Okay, so from there, you just remember the equation, and can you see? No, I think so. Let's leave it. Yes, this equation is for the spherical coordinate. So, as it is a steady state equation, so del t term will be cancelled out. There is no convection, that means left hand term all will be cancelled out, right? For mass transfer. So leave it. So we'll be writing this for mass transfer, remember. Sorry, it is not called Navier-Stokes equation because it is Navier-Stokes. It is similar like Navier-Stokes equation. You have not studied the Navier-Stokes part yet. It will come when you solve the momentum flux. So from next week onwards, you will be solving the momentum flux. Till today, it is the till week 3. It is the mass flux related equations, right? So next you will learn the Navier-Stokes. It is a spherical coordinate equation for mass transfer. So from the huge long equation, we'll be only considering the diffusion at the in radial direction. That is what is left. So what is left? So this part is left from the whole equation. If you have the whole equation, you can definitely look into that. So it is minus di 1 by r square into del r del r of r square into del ci del r, okay, equals to Ri, because what is said that there is a steady state diffusion reaction is there, right? So now the only variable is r, so we can write it in the form of differential equation, not the partial differential equation, right? So it is minus di 1 by r square ddr of r square dci dr equals to Ri. So for the reaction, for any kind of enzymatic kinetic reaction, basic equation we have studied from, we know that is the Michaelis-Menten equation. So we considered it as Vmax by Kmax. Also you can write it as S. Okay, write this as X. So write it as S. S is the substrate concentration. That means whatever is coming in the pellet, that enzyme is immobilized in the pellet, and there is a reaction associated with the enzyme. So it is K Vmax by Kmax plus S. Okay. Sorry, Vmax X S K by Kmax. So these are the rate of the enzymatic equation. Okay. So we are not interested in that. We are not going to learn the chemical reaction engineering. So it is the basic form of modeling in the mathematical expression. It is the basic form where you can express your enzymatic reaction that is happening in a biological system, right? So now if you just multiply this, express this, so it will be minus, this is minus d effective also you can run, right? It is effective diffusivity. So two terms are there, so we will take the derivative of it one by one. So it will be d2s dr2, right? Plus, so we'll keep constant the dr and r square, and we will take ddr of r square. ddr of r square is minus 2r. So minus 2r by r square, it will be minus 2 by r ds dr equals to same. I am writing Vm and Km. Okay, don't confuse it. Vm is by Km plus S. Okay. So it will be plus because minus is already downside. So it's not minus 2r, sorry, it is 2r. Extremely sorry. Okay. So now we'll go to the next part. So now we'll express. So there is a boundary condition associated with it. So what is the boundary condition? That means suppose this is a pellet, spherical pellet. So at r equals to 0, that means at the middle, at r equals to 0, there is no change of concentration. So ds dr will be 0, right? And at r equals to r, suppose this pellet radius is r. So at r equals to r, substrate concentration is 0 at the initial. Okay. So now we'll do the non-dimensionalize, because as you can see that it is a very complicated form. You cannot solve it directly. So we will non-dimensionalize these things. Non-dimensionalize. How we'll do that? So we'll take x as a ratio of S by S0, the substrate concentrations, and we'll take y as the ratio of radius. So it is r by capital R. Okay. So this non-dimensionalized number, or how can we non-dimensionalize it? It will change with the problem. So here we want to find, here we have two variables, like one is r, which is the independent variable, and S is a dependent variable, right? So how the concentration changes with respect to the radius we want to see here. So we are taking this non-dimensional number or non-dimensionalize this with basis of this. So whatever will be our objective of a problem, that's how we'll take the non-dimensionalize. We'll define that function and it will be changing for different cases. Okay, so this is x, this is your y, right? So now we can take, we'll do the ds dr term. We'll calculate ds dr equals to, so now you can see that ds and r is not equal, directly related. So you cannot take differentiation of ds and dr. So we'll partialize. So we have seen that x is in form of s, right? So we can take ds dx. Now x is also directly not related to r. So what we can take? It is related to y. So we'll take dx dy, right? And now we can understand that y is related to r. So dy dy. So if you know chain rule, if you have studied chain rule, you can understand this, right? So ds and r is not directly related. Sorry, it is smaller. So we can write it in this way. Now ds dx, what it is? So it is s0. Only s0 is left, right? So dx dy we don't know, and dy dr is 1 by r, right? So it will be finally s0 by r into dx dy, right? Remember this. Next term will be, because two terms are there, d to s dr2, right? So it is nothing but d dr of ds dr, right? So how can we write? Again the same problem. So we can write it as d dy of ds dr, and again here it will be dy dr, right? And now we have the value of ds dr here, right? So what we'll write? So d dy of dhdr is previously we have calculated is s0 by r into dx dy. So it is s0 by r into dx dy and dy dr, right? Now as you can see, or dy dr has already value which is 1 by r, right? So it will be, so s0 by r and 1 by r the constant, so it will be s0 by r square, and this will be simply d2x dy2, right? Any confusion is there? Just simply mathematics. Okay. Now we have known the term, so we'll put back these two terms in the equation, that is this equation, right? This equation. This is our goal. We want to solve this equation, right? So we'll simply put it back. So what are the terms coming? So there is a minus d effective. It will be, so d2s dr2, it will be s0 by r square d2x dy2 plus s0 by, what was there? Another term was 2 by r, right? So 2 is 0, right? 2 is 0 by r square, because already r is there. It is dx dy equals to, and now you know that s is nothing but the s0 into x. Here you have defined already, right? And r is your yr. So we'll simply write that. So it will be s0x divided by km plus s0x, right? Now we are dividing by minus df s0 by r square. Okay, the whole term we are dividing it through the whole equation, right hand side and left hand side as well. What is coming? So from the first term, simply this term will go away. So it will be d2x dy2, right? Simple. In the second term also, it will be just, so there is a y because it is small r there. Yeah. It will be just plus 2 by y dx dy, simple, equals to minus, so we are defining it, so it will be minus Vm. So we are defining S0 is already there, S0 will not be there, so it will be x and it will be r square, because we are dividing it. This term is not present here, so we have to multiply it, divided by df. We have to take it here into km plus s0x, right? Simple. Is there any confusion? I hope not, right? Similarly, you can write the equation in its other way. So d2x dy2 plus 2 by y dx dy equals to minus. So all these terms are coefficient. Vm, df and km, right? So it will be Vm r square. These are given. Df into km. If you take common of the km, what will it be? It will be x will be as it is there. So it will be 1 plus s0 by km into x, right? This is just a mathematics, nothing else is there, right? You got it, right? So now, in the next step, we will define the Thiele modulus, which is similarly defined in the equation in the lecture. So it is Thiel modulus MT is the ratio of reaction rate divided by diffusion rate. Okay, so it is reaction rate. Reaction is defined by R cube V max by Km into S0, and diffusion rate is defined as R dF into S0. So what is coming? So if you just cancel it out and one R is cancelled out, so it will be V max or Vm, you can write for easy to understand. Vm R squared by dF into Km, right? Can you spot this term here? You have spot the term here, right? It is the same term. So we will simply just replace this term with this. And there is another term which is the beta, okay? Which is beta, which is defined as S0 by Km, okay? Now we will put this value in the equation. So what it will be? So we will come to beta, that how will we solve it. So it will be d2x dy2 plus 2 by y dx dy equals to minus mt into x by 1 plus beta x. We just replace the terms, right? We just replace the terms. Now, what will be the boundary condition if we want to solve it, right? So as we know earlier, that r equals to 0 means, or at r equals to 0, ds dr equals to 0. So now if you remember, r equals to 0 means y equals to also 0, because y is nothing but small r by capital R. So y equals to 0, and also you have expression of ds dr, right? So ds dr expression is here, is 0 by r into dx dy, right? So ds dr 0 means dx dy also 0. And at r equals to r, s equals to s0, right? So now if you remember, so y equals to 1 because it is capital R by capital R, okay? Y equals to 1, and s equals to s0 means x is also 1, right? Do you remember? So these are your new set of boundary conditions, okay? Now if we want to solve this, still it is difficult to solve, right? So for that we will consider, so we have said that beta is S0 by Km, right? So if S0 is less than Km, so beta is very small value, right? Beta is very small value. So then we can consider it as first order kinetics. So that means the enzyme is following a first order kinetics, right? And if S0 is large than Km, then beta is large, beta value is large. So then we'll consider it as zero order kinetics. Zero order kinetics, the enzymatic equation is followed. So now first we'll do it. So from the next part, it is completely mathematics, okay? Nothing is related to the transport phenomena. This is the complete mathematics. The solve is not shown in the lectures, that is why I am showing here. Okay, so now we'll consider as beta is very small, that beta is almost 0. So how will you solve it? So beta is, suppose it is a suppose first order kinetics is followed. Okay, so beta will be 0. Okay, so now what is left in the equation? So you can see that this beta will be 0. So everything will be left out. So it will be d2x dy2 plus 2 by y dx dy minus mtx equals to 0. We have kept the negative sign this side also because the radial concentration is of the substrate is going from outside to the inside, right? That is why, and we have always considered that positive direction is from the inside to outside, but we are going here from outside to inside. That is why we are keeping it minus even in the left hand side of the equation, right? This is the final equation. So still you cannot solve this equation. So we need to take another thing, another approximation. So suppose we are defining u into xy. Okay, that means x will be u by y. Right now we'll be putting these values. So if x is u by y, it will dx by dy will be, if you do it, it will be 1 by y du dy first term, and second term will be minus u by y square, right? Do you agree this? Just simple mathematics. Next, we will define the d2x dy2 term. So it will be the differentiation of this complete term, right? So it will come 4 term. So it will be 1 by y d2u dy2 minus 1 by y square du dy from the first term. Okay, from this first term, 2 differentiate term is coming, and if you differentiate this term, again 2 different term will come. So it will be, the first term will be similarly 1 minus 1 by y square du dy, and the last term will be 2u by y cube. So these two terms are same, right? So we'll just simple write it. So d2x dy2 will be 1 by y d2u dy square minus 2 by y square. We have just added those two terms, du dy plus 2u by y cube, right? This is the expression. Now if we put this expression in the original expression what we have considered, so this is our new expression, right? This is our new expression, right? So we are putting these values there. So I'm taking a new pen to make it look good. So now what I just simple put it, so it will be 1 by y d2u dy2 minus 2 by y square du dy plus 2u by y cube. Okay, plus the second term was 2y du dx. The second term was 2y du dx. Sorry, dx dy. So we multiply 2 by y dx dy. So this is your dx. So it will be 2 by y square du dy. First term will be 2 by y square du dy, and the second term will be minus 2u y by y cube. Okay, and now the last term empty x was there, so x will not x, we will write it as u by y equals to 0. Okay, so now you can see that these 4 terms will be cancelled out automatically, and it will come as, so we can take it out 1 by y, so it will be simply d2u dy2 minus mtu equals to 0, right? Simple. Now if you solve this equation, it has an universal solution. I am not showing you how this equation is again solved because it is similar way it will be solved. You have to take u as any function and then you can solve it. But still you can write it directly because it has an universal solution. So that universal solution is u equals to c1 sine hyperbolic root mty plus c2 cos hyperbolic root mty. Okay, simple. Now you will put the value. So u was x into y, right? So x will be c1 sine hyperbolic root mty plus c2 cos hyperbolic root mty divided by y, right? So from the boundary condition we have seen that y equals to 0. At y equals to 0, dx dy equals to 0. That means x is a finite value, right? So we will take limit in both direction. So if you take limit of this x at y tends to 0, so we will see that, so we know that cos hyper at limit tends to 0, limit y tends to 0, c2 cos hyperbolic root mty by y also tends to 0 because cos hyperbolic value will be 0 at 0. So it will be infinity. Sorry, I mistaken. This will be 0 and y is at the bottom. So it will be infinite. So it will be a huge term, right? So we will neglect this term. So our final term will be x equals to c1 sine hyperbolic root mty by y, right? Now we'll put the second boundary condition. What was that? Y equals to 1, at y equals to 1, x equals to 1. So what will be the c1? c1 will be 1 by sine hyperbolic into root mt because y is 1, right? Now if we put this value, put this c1 in the equation, so it will come as x equals to sine hyperbolic root mty divided by y into sine hyperbolic root mt, right? So this is your xy equation. And now if we put the values of x and y, so we have earlier taken x equals to s by s0 and y equals to small r by capital R. So it will be, so s will be s0 into capital R by small r sine hyperbolic root mt r by r divided by sine hyperbolic root mt. So this is the final equation between the distribution between the substrate concentration with the radius of the pellet, right? So this you can put and you will get the graph. Now, if beta was a large value, if it is a zero order equation, if beta was large value, then we will see non-linear term will come, right? Non-linear term will come because you have seen that here in this equation, so this equation x and beta x is there, so this term is a non-linear term, so it cannot be solved. So it cannot be solved simply. So So it will be non-linear ODE. It can be solved and it should be solved because it in simple numerical solution or analytical solution it cannot get. So it is can be solved by numerical method. So we are not going into that because that is not our motive here. Okay. Now next comes the effectiveness factor. Next important term is the effectiveness factor. So E theta is actual mass transfer reaction rate, actual reaction rate when there is no actual reaction rate, what is when there is a presence of mass transfer, and divided by reaction rate in the absence of mass transfer. Okay. So if you put these values, the details is given in the lecture. I am not going into that. So finally, what we will get as the eta value. So eta derivation is given in the. I am not repeating it. Okay. So it is dx dy at y equals to 1 divided by mt, that is a Thiele modulus, by 3 into 1 by 1 plus beta. Okay. This is the effectiveness factor. Next important is the unsteady state diffusion, but I am not doing it right now because also it is given in the lecture. If time permits at the end, we will do the derivation. The derivation is given in the lecture step by step, but still if you have any confusion, because these are the little tough or little lengthy basically. It is not tough. It is very mathematically juggling. Otherwise, very easy. It is a bit lengthy, so we will do it later. But first, we will do the question answer. Okay. So we will do the question answer section. So a silicon tube is used to carry CO2 to aid a laparoscopic renal surgery. Silicon tube is known to have a higher permeability to CO2. Assume that the mass transfer occurs only via radial diffusion and there are no convective currents. Identify from below the equation for mass flux through the walls of the tube to the environment, given that the thickness of the tube wall is 1/10 the inner diameter and the concentration of CO2 in the lumen does not vary with time. The concentration of CO2 in the lumen is Ci. Ri is the inner radius of the lumen. Okay, so we have to derive it. So how are we going to derive it? So it is said that it is radially going and it has outer diameter which is 1/10. This portion is 1/10 of the inner diameter. Inner diameter is Ri. Okay. So what we will do, and it is also a steady state diffusion. Okay. So for cylindrical coordinate. For cylindrical, the flux is defined as, you have to do it, but I am not doing it here. From the first lecture, you can do it, okay? Let me check. So the derivation will be this. I am not doing it because of the time constant. I have to make you solve the question. So it is in the lecture. Okay. So this derivation, whatever this derivation is given here, right? It is the same. What we are going to solve it here. And you solve it by yourself. Okay. I am not solving it. You solve it by yourself. And your final expression will come as this. DAB K CB minus C0 by RB into ln RB by R naught. Okay. So we'll directly write this equation. So this mass flux of CO2 will be JCO2 star will be it will be DCO2 air. This is the diffusivity. This is the diffusion. So K is your coefficient, dissolution coefficient, right? And the temperature that concentration gradient will be C0 by Ci, because it is said the in concentration, the lumen is Ci, okay, divided by Ri is the inner radius. That case Rb was the inner radius. Here Ri is the inner radius into ln Ri by Rl, outer radius. You have to do it because otherwise you cannot do it. If you remember the equation at the first, derivation at the first, let's say it's a diffusion for cylindrical coordinate. From there, this expression is coming. I am not doing it. You do it yourself, okay? Because the derivation is clearly done in the class or in the lecture, okay? So now, what is RL? Okay, will you confuse it? It will be RO, that is outer radius by inner radius. Yeah. Just a minute. I'm checking the equation with the signs. In the definition, you have to see the This is not here. Huh? Where is that one? So RB is the inner radius, right? Yes, RB is the inner radius. That's why the confusion came. RB is the inner radius and RI is the inner radius and RO is the outer radius by RI is the inner radius. Okay. Concentration of CO2 in the lumen does not vary with time. Okay, this is fine. So the outer radius is defined as R0 equals to inner radius plus 0.1 of the inner radius. So it is the 1.1 Ri. So now if you take it like 1.1 into Ri, so it will be ln 1.1, right? So value of ln on 1.1 will be value of ln 1.1 will be 0.095. So value of ln 1.1 will be 0.095, right? So simply the equation will be dCO2 AR Ka into CO minus Ci by 0.095 Ri. Okay, so it is option 4. I hope you have understood it. Just simply follow the first lecture. It will directly come from there. Next. Question 2 was a bipolar composite was developed in a laboratory with desirable properties to deliver the drug to the colon. The developed product was pH responsive in an experimental setup to analyze its applicability. The drug was infused into the spherical polymer beads and its swelling property was studied in solutions of different pH. If a shell balance approach is used to derive the expression for diffusion of the drug through the beads under steady state, which of the following shells would be the best choice and what would be the boundary conditions at t equals to 0? Given radius r is r, capital S is the concentration of drug inside the pellet. So it is a spherical, right? So spherical shell balance approach will be applied. So it is said that at t equals to 0, the drug is uniformly infused throughout the pellet interior, giving the initial concentration C in for R less than R. Okay. So this is the, so for spherical, it is spherical. At t equals to 0, C will be in. So it is option A. Simply option A. Okay. So at time t equals 0, drug is already infused and it is infused uniformly inside the pill. Okay. Next. At time t greater than 0 of drug elution, the drug is eluted from the beads in alkaline pH. Identify the boundary condition that represents this phase of drug elution without any resistance from the surroundings. So, initially it is said that it is spherical, right? So, we will consider that due to radial symmetry, the concentration profile, the concentration C or concentration profile must be symmetric. Because it is uniformly spreading. Must be symmetric because the drug is uniformly spreading in all directions, right? So it will be zero flux at the boundary. So with time, so when t equals to 0, t greater than 0, when t greater than 0, del C del R will be 0, right? Because it is zero flux. It is saying it is zero flux. Because it is already, so at the boundary there is no change of concentration with radius. So it is 0. So at t greater than 0 with time, as time increases, it spreads uniformly. So del C del R will be 0. And when it reaches the boundary, del C del R equals to 0 at R equals to 0. So at the middle, because it is diffusing very clearly, there is no mass transfer. So at the center, the concentration change is 0 with time, right? And the concentration will be at its maximum at R equals to R. So C will be C infinity at R equals to R. That is at the boundary. Because the drug elution is happening here. Okay. So this is option D. Next. Animal studies were carried out to test the efficacy of the above biopolymer. In drug delivery and to check for unwanted side effects. A drug which acts in the intestine was entrapped in the spherical polymer and tested in an animal. The polymer was found to effectively release the drug at the targeted site, which is seen through the increase in its bioavailability. The drug, once released, is known to take part in a reaction of first-order kinetics. If we do a steady-state material balance on the spherical biopolymer, which among the following do we get as the governing equation? CD is the concentration of drug at the pellet. So steady, it is also steady state and it is spherical, right? Spherical polymer, steady state. So it will be similarly like minus d effective. If you remember the derivation we have done here, minus d effective 1 by r square. This is the similar one. It will be similar one. Okay, the left hand side will be exactly similar. So we'll write it directly. Minus d effective. We are not doing the derivation here. So it will be the concentration of drug is given. So it will be D2CD by dr2 plus 2 by r, right? Here also it is there. So it is coming from the first step itself. Here to here. From here to here, how it is coming? It is coming like this. Okay. So 2 by r dCd dr equals to, there it was an enzymatic reaction. The substrate was going through an enzymatic reaction, right? But here it is not any enzymatic reaction. Here the substrate is going through a first order kinetics, right? So it is first order kinetics is K into Cd, simple. So if you compare, it is option A, right? The drug delivery using the above biopolymer had a Thiel modulus of 24.26. As stated previously, the drug takes part in a reaction of first order. Which of the following is true? Consider the definition of the Thiel modulus. So, we have seen that Thiel modulus definition is given as reaction rate to the diffusion rate, right? Right? So when MT it is given as 24.26 is greater than 1, so it means it is reaction dominated. It is reaction dominated. So it is option C. Reaction is fast but limited by diffusion. Okay. Next. The ratio of actual reaction rate to the reaction rate in the absence of mass transfer resistance is termed as effectiveness factor. We have defined it, right? Next. Which of the following continuity equation denotes an unsteady state diffusion? So unsteady state diffusion needs this. So there will be no equal to. So in unsteady state diffusion, it is simply, it will be del Ci del T equals to di del 2Ci del x2. This is the equation. So it is option B. Next. Pseudo steady state approximation is normally used in comparing two processes of widely varying rates, comparing two processes of equal rates, processes not varying with time, processes following only zero order kinetics. So we have seen that, so it is comparing two processes of widely varying rates. So you can only define it like a train is going at certain speed or certain rate, right? So this rate cannot be, this train engine rate cannot be dependent on how much time the train took to build, right? So that rate cannot be related to that how much fast the train runs, right? So these processes are comparing, we are comparing two different processes here, and their rates are completely varying. So one rate is not affecting the other. Basically, that those two rates are independent of themselves. That is why we call it pseudo steady state approximation. So it is comparing two processes of widely varying rates. Next, a group of microbiologists discovered an endolithic aerobic bacteria. The bacteria survived in the center of a porous rock. Owing to the fact that the permeability to oxygen was deeply affected by porosity and tortuosity of the rock, the concentration of oxygen inside the rock varied with time. However, the bacteria had adapted itself to the situation over many years by slowing down its metabolism and reproduction rate. Hence, the changes in the concentration of oxygen with time did not affect the bacterial metabolism. Now, if the diffusion of oxygen to the bacterial cell had to be modeled with an aim to study its growth, which of the following statements would be ideal to consider? CO2 concentration of the oxygen. So, as you have seen that over the time, the bacterial adaptability to the metabolism has changes, right? It has slowed down the metabolism throughout the years. So that is not related to the phenomena that oxygen is coming through the porous rock. Oxygen is diffusing through the porous rock. So the rate of oxygen diffusion through the porous rock is not related to the slowing down of the metabolism of the bacteria, right? So as just now I have given an example of the train, right? So these two processes are completely separate. So we can now take as the steady state, pseudo steady state approximation. So it will be pseudo steady state equation. So dCO2 dt inside the rock will equals to 0. So inside the rock, the concentration of oxygen at pseudo steady state approximation is possible here. It is option B. Next, in the above example, the entry of oxygen in the cell is affected mainly by the permeability of the rock and the permeability of the cell membrane. In the absence of estimates of the above permeabilities, which of the following strategies can be adopted to represent the total permeability? So, the resistance, the rock permeability of the rock and the permeability of the cell membranes are serially connected if you think. So total permeability will be 1 by P T equals to 1 by PR plus 1 by PC, right? So it is option A. Next, fungal cultures were used to produce industrially important lipase enzyme in a shake flask study. Aeration and mixing were ensured by using a shake flask incubator at a set RPM. At these culture conditions, the fungal growth is pelleted, and this morphology was associated with increased production of lipase up to 2 days, after which a reduction is observed in spite of increase in the pellet size. This increase in size restricts the diffusion of oxygen and nutrients to the center of the pellet. There is also reduction in available nutrients in the medium with time. Identify from below the governing equation for the diffusion of the nutrient N across the pellet thickness X. So it has said that due to change in the pellet size, nutrient concentration changes with time, and also lipase generation is affected at the center. Generation is affected at the center. That means the nutrient concentration is varying with time and with concentration also. So this is simply option B. Next, effectiveness factor is defined as the ratio of actual reaction rate to the reaction rate in the absence of mass transfer resistance. So it is option A, as you know. Next, permeability is defined as from the definition you will know that permeability is defined as dK by L. So it is proportional to the molecular diffusibility partition coefficients and inversely proportional to the membrane thickness, dK by L. It is option C. Next, kombucha is a fermented tea drink prepared using a symbolic culture of bacteria and yeast. Other than the claimed probiotic value of the fermented drink, one important byproduct obtained from this fermented is the cellulosic biofilm produced by acetic acid bacteria. It contains pure cellulosic fiber and has properties enabling its use in tissue engineering applications. Okay. Tissue engineering applications. Consider a bacterial colony in one such fermentation process producing the biofilm. The entry of the nutrients in the cell is affected mainly by the permeability of the biofilm and the permeability of the bacterial cell membrane. Which of the following strategies can be adopted to represent the total permeability of the biofilm membrane combination acting in series? So it is the same. So it is option 2. 1 by Pt equals to 1 by Pb plus 1 by Pc. The immune response to a retroviral infection is modeled mathematically in a study aimed at understanding the dynamics between viral replication, immune response, and rate of infection. The susceptible host cells are infected at a rate AX units, and the rate of change of immune response is directly proportional to the infection rate. The viral replication is inhibited at a rate IY+1 units via immune response. Immune response is a result of the combined effect of the number of infected cells and the load of free virus. It is observed experimentally that the virus is fast replicating, and the rate of replication of free virus is much faster than the rate of infection and rate of inhibition combined. The Cn is the concentration of free viruses. Which of the following is a possible assumption to model the immune response? So as you can see, as you can see, right? So as you can see, the replication of free virus rate. So it is the replication or concentration replication of free virus rate is much higher than the rate of infection. So this line, rate of replication of free virus is much faster than the rate of infection and rate of inhibition combined. So we can consider it as the pseudo steady state. So it will be, so the concentration of replication of free virus with time will be 0, because pseudo steady state approximation is possible here. Viral replication is a faster process. Next, in the context of steady state diffusion across a tubular bronchial wall, if the partition coefficient is K, the concentration in the lumen is Cb and the concentration in the tissue is Co. What are the boundary conditions for the drug concentration Ca at the inner wall Rb and outer wall Ro? So, Ca concentration at the inner wall, Ca concentration at the inner wall, that is Rb. So at R equals to Rb, Ca concentration will be dictated by the partition coefficient and at the concentration of lumen, and at the outer wall concentration Ro, Ca will be Kc0. So it is option B. Next, for a porous spherical ceramic pellet releasing growth factors into the soil, the steady state release rate moles per time is derived as 4 pi di COI. If the radius Ro, if the radius R of the pellet is doubled while keeping the surface concentration C0 and diffusivity Di constant, how does the release rate changes? So release rate is proportional. Release rate is proportional to the R, radius of R, as you can see from this, right? So if Ci and Co and Di are constant, then If the R is doubled, this is also doubled. It doubles. That is red doubles. The Thiel modulus is defined as a non-dimensional parameter used in analyzing diffusion with reaction. What ratio does it primarily represent? It is the reaction rate by the diffusion rate, option C. Next. In the analysis of unsteady state diffusion for surface modifying agents, a similarity variable eta is used to convert a partial differential equation into an ordinary differential equation. What is the expression of eta? So in the unsteady state equation, if you see lecture probably 15 and 16, you will study the unsteady state diffusion part. Unsteady state diffusion lecture, if you see, so eta is defined as z by root under 4 dit. Okay, so it is option C. Next, according to the pseudo-steady state approximation, when comparing two processes with widely varying rates, which process can be assumed to be at steady state? This is the faster process. Right? So that's what I said, right? The train that the engine, how much the engine took time to build and how much the one part of the train took time to build is not related to one another, right? So we will consider the faster process. Next. When modeling resistances to mass transfer of a coated membrane, how are the individual permeabilities combined to find the total permeability? So it is option B. Many times we did, it is option B. Next. The effectiveness factor for an immobilized enzyme reaction is defined as the actual rate by rate without mass transfer resistance. Next, in the derivation of unsteady state diffusion, the solution is expressed in terms of which mathematical function? So this theta is, if you solve the derivation, you will find that it is defined at the form of complementary error function. Because finally you will get an expression like this. Theta equals to Ci by minus C naught by Cs minus C naught equals to error function of eta, that is Z by root under 4 dit. Next. When applying a mass balance to a spherical pellet at steady state with reaction, which coordinate system terms for velocity are typically set to 0 if there is no bulk fluid motion. So it is all of them. So there is no convective term present, right? So all of the bulk motion velocity, bulk velocity will be 0. Next, you can write it like no convective term. A cylindrical bronchial wall has inner radius Rb equals to 0.5 millimeter and outer radius R not equals to 1 millimeter if the concentration profile is like this. What is the primary independent variable for the diffusion process? It is the radial distance R, right? Diffusion is happening with respect to the position, so it is R. A cylindrical drug-eluting stent of length L has an inner radius Ri and outer radius Ro. If the steady-state concentration at the walls are Ci and Co, respectively, what is the correct expression for the total molar flow rate? So you have to apply the Fick's law for a cylindrical part, and then you have to put the concentrations and then need to calculate the flux, right? So if I have to do it, it will be simply like the cylindrical coordinate. From cylindrical coordinate, term will be di 1 by r del del r of r del c I del r equals to 0, right? So it is said that r equals to ri, it is ci. So this, suppose this is C, so C will be Ci and R equals to cap Ro, it will be C equals to Co. So if you just give a solution of it, it will be coming as R dCdr equals to A, which is a constant. So now if we want to calculate it, so C will be A ln R plus B, and if you put the values, so it will be Ci equals to A ln Ri plus B, then Co equals to A ln Ro plus B. So if you take the minus side of it, if you take the negative of it, it will be like Ci minus Co equals to A ln Ri by Ro. B will be cut out. So A will be Ci minus Co by ln Ri by Ro. Now if we put the value, C will be Ci minus Co by ln Ri by Ro into ln R, right? So now if you take the flux of it, so flux will be J equals to minus DAB or minus DI or minus D, just write D, dCdR. So question was for total molar flow rate, right? So at suppose R equals to Ri, I am talking about Ro. So minus D dCr dI will come from here, Ci minus C naught by ln Ri minus R naught by ln R means 1 by R. So it will be minus D Ci minus C naught 1 by R, that is R naught ln Ri by R naught, right? Now if you multiply this with or D equals to Ci minus C naught R naught ln R naught by Ri. Now if we multiply to calculate the release rate with the cylindrical wall, so it will be J into its the surface area, right? The layer has length L, right? So it is the outer surface area. So it will be 2 pi into L, right? So it will be 2 pi L, J will be D I Ci minus C naught by R0 ln Ri by ln R naught by Ri. Ln R naught by Ri. So this term is option C. So though I think one R naught is missing, but still it is close to that, right? Next, a spherical ceramic pellet with radius R is used for nutrient release. If the diffusivity is this and the surface concentration is this, calculate the steady state release rate WA into a medium where the concentration at infinity is 0. Spherical, so W will be the release rate will be 4 pi R then Cs into R. So this equation is coming from the spherical diffusion. Okay, if you see, you will find this. It is the spherical pellet release rate. Okay. Diffusion, so this is radial diffusion in spherical pellet. Option 2 I have shown in the first, and it is a release rate is this. So now the diffusion is given, or there is D. Sorry. This is D. Diffusion. Diffusion rate is given dA, and the concentration Cs is also given. So it will be like 4 pi dA is 10 to the power minus 5 into 0.5 into 0.2. So it is coming as 1.256 into 10 to the power minus 5 mmol per second. So it is close to option B. An immobilized enzyme pellet has a radius R, diffusivity D, and a first order reaction rate constant K. If the radius of the pellet is doubled, how does the Thiele modulus MT change? So in the MT expression, if you remember the expression, it was sort of Vm where was that? Thiele modulus. Vm R square by D effective into Km, right? From this expression, so MT is proportional to R square. So if R is double, it will be 4 double, like quadruples. Option D. Next. For a system with very large Thiele modulus, what is the approximate value of effectiveness factor for a porous catalyst slab? Okay. So these are defined. Porous catalyst slab eta equals to tan hyperbolic MT divided by MT. Okay. So if MT is infinite, that is, so tan MT will be 1, theta will be 1 by MT. So it is option D. So if MT is higher, so tan hyperbolic MT is close to 1. So eta will be 1 by MT. Next. In unsteady state diffusion into a semi-infinite medium, if the time t is quadrupled, how must the distance from the surface Z change to maintain the same value of the similarity variable eta? So eta is Z by root under 4 dit. If time is quadrupled, that means time is 4t. So time is, so eta is proportional to 1 by root T. Or we Z is proportional to root T, right? So if how the Z change, it said na. So if T is quadruple, so it will be Z 4T. So Z will be proportional to 2 root T, right? So Z must be double. Z is also must be double to keep the eta same constant. So it will Z must be double. Next, two membrane layer are placed in series. Layer A has thickness L1 and diffusivity D1. Layer B has thickness L2 and diffusivity D2. What is the total permeability P of the composite structure? So P is defined as dK by L, right? So permeability will be 1 by P equals to L1 by D1 plus L2 by D2 because there is not the coefficient, and there is no presence of the coefficient, and we have to calculate the permeability in a series like this. It's option B. Next. Using a pseudo-steady state approximation for a surface modifying agent of density ρ and initial thickness L, the time to evaporate was derived as T dry equals to ρl square by 2 di Csat. If the initial thickness L is tripled, how the T dry is affected? So it will be ninefold, obviously. For a first order reaction in a spherical pellet, the effectiveness factor eta is this. What is the value of eta as a Thiele modulus empty approaches 0? As empty approaches 0, empty approaches 0, that means there will be no mass transfer resistance, like there is no diffusion resistance. No diffusion resistance. So effectiveness factor, which is the ratio of actual reaction rate or mass transfer rate in absence of reaction rate in absence of mass transfer resistance, so it will be equal. So it will be 1. Eta will be 1. Next. In a cylindrical coordinate system for steady state diffusion, 1 by r ddr into r dc equals 0. If the integration constants are C1 and C2, what is the general form of the? So just now we have seen, so it is option D. So we have shown you this in here, right? Where is it? Here. No. Here it is. Yes. So it is the same expression. It is coming like this. So it will be C1 ln R plus C2. So Ca will be C1 ln R plus C2. It is option D. Next. A drug is diffusing through a tissue layer. If the partition coefficient K is C tissue by C fluid is 0.8 and the fluid concentration is 2 mole per meter cube, What is the concentration Ca just inside the tissue? So just inside the tissue, Ca will be K into C fluid. Okay. So K is 0.8 into fluid concentration is 2. So it will be 1.6 mole per meter cube. So these equations are little, this question are little big, like 36, 37, 38, 39. Okay. So I'm not going to do this right now. Let's do some more problems. Then if time permits, we will do this. Or else we will do it later. Okay. Or also you can try by yourself. Okay, no issue. Just a minute. Hmm. A hydrogel hollow fiber of length L, inner radius R1 and outer radius R2 is used for steady-state radial nutrient diffusion. The inner wall is maintained at a concentration of Ca1 and the outer wall is maintained at Ca2. The effective diffusivity of the nutrient is Df. Calculate the total molar transport rate across the cylinder shell. Okay, so there I have done a single mistake, then you'll understand why it is here like that. Here, no, it was here. So it is the outer shell is 2 pi RL, right? 2 pi R is the outer surface area of a cylindrical is 2 pi R. Outer diameter it has to be, so it is R0. So if you multiply, so R0 will cancel out. So it is the same. So this equation we need to use here because this steady state cylindrical diffusion is asked, right? Steady state cylindrical diffusion. So the expression we know. So it is WA expression is 2 pi L D effective Ca1 minus Ca2. That means inner versus out minus outer. Divided by divided by Ln. Outer radius is R2 by inner. Right now, if we put the values, we will get. So what it is coming? So you just tell me the value final. So ln, first we'll calculate ln R2 by R1. So ln 1 by 0.5 is 0.693. 0.693. Okay, so now calculate 2 into pi into L is 0.1. D effective is 1 into 10 to the power minus 9, and Ca1 minus Ca2, that is 2 minus 0.5 divided by 0.693. So it is coming as 1.36 into 10 to the power minus 9 mole per second. So for the unit also you can check. So it is meter, it is meter square per second, it is mole per meter cube. Bottom one is dimensionless. So it will be mole per second, right? Next. An enzyme is immobilized inside a spherical biocatalyst pellet of radius r. The internal reaction follows first-order kinetics with rate constant K1. The effective diffusivity of substrate through bead is dF. Calculate the dimensionless Thiel modulus using this. So Thiel modulus is so it is pi equals to r is 0.5 into 10 to the power minus 3 root under K1 is 16 by dF is 10 to the power minus 9. 1 into 10 to the power minus 9. So it is coming as 16 by 10 to the power minus 9 root under this into 0.5 into 10 to the power minus 3. So it is coming as 63.25, which is greater than 1. State whether the process is the pellet inside the pellet is reaction controlled or the diffusion limited. So it is the reaction rate is too much high, so it is strongly diffusion limited. So it is diffusion limited. Okay, next. For a spherical biocatalyst operating in a strongly diffusion limited regime, the effectiveness factor eta can be approximated by the simplified asymptotic reaction. Suppose a catalyst bead has a Thiel modulus of 15. The intrinsic reaction rate at surface condition Ca0 is R, A equals to 100 mole per meter cube second. Calculate the effectiveness factor eta. So eta is given as 3 by 5. So it is 3 by 15. It was 0.2. Compute the actual diffusion limited reaction rate inside the sphere. So our A actual will be eta into our diffusion limited reaction rate. The surface is given, right? Reaction rate at surface. reaction rate surface is given. So it is coming as eta 0.2 into 100. So it is coming as 20 mole per meter cube second. Okay. This is your actual diffusion limited reaction rate inside the sphere. Next. A spherical microcapsule has an inner radius R1 and outer radius R2. The core contains a drug at constant concentration Ca1 with the outer surface is continuously washed, so Ca2 is 0. The drug diffusivity through the shell is dF. Calculate the steady state drug release rate WA using the spherical shell rate formula. So we know the spherical expression, right? Spherical expression is coming from di 1 by r square steady state, right? Del r square del ci del r equals to 0. So if you integrate, it will come as r square dci dr equals to a1 a maybe, or ci will come as b minus a by r, right? Now if you take the boundary conditions, what are those? At r equals to 1 millimeter, Ca1 is 10 mole per cube. As r equals to r1 or r1, Ci equals to Ca1, and r equals to r2, Ci equals to Ca2. We'll put the values later. So now if you put this, so it will be Ca1 equals to b minus a by r1, Ca2 equals to b minus a by r2. So if we differential, we take subtraction. So C1 minus Ca2 will be a by r2 minus a by r1, right? So a will be Ca1 minus Ca2 divided by 1 by r1 minus 1 by r2. Okay. Now what will be the b? So if you put the value, Ca1 equals to b minus Ca1 minus Ca2 by r1 into 1 by r1 minus 1 by r2. Right? So it is said that Ca is 0, right? Ca2 is 0, right? So here also I can write Ca2 is 0. So Ca1 will be this. CA1 will be, how come? 1 minute, just a minute. Hmm, CA1 minus 0 is CA1, B minus B cancelled out. So minus A by R1 plus A by R2. So we are taking A common, so it is 1 by R2 minus 1 by 1. So A will be CA1 okay into 1 by R2 minus 1 by R1, sorry. And we do not calculate B from here, we'll calculate B from the next equation. So B will be minus A by R2, right? So it will be minus, so you can write it as CA1 divided by 1 by R1 minus 1 by R2. We are taking the minus here. Right? So next C will be, so Ci expression will be CA1 there will be an R2. CA1 by R2 1 by R1 minus R2 minus CA1 divided by R into 1 by R2 minus R1. Okay. Okay. So now we'll take, or else we can write it as CA1 by 1 common 1 by R1 minus 1 by R2. So it will be just simply 1 by R2 plus 1 by R. Okay. Now if you take Ji will be minus DAB or DAB, DCI dr, right? So DCI dr, so DCI dr will be C A by 1 minus R1 minus 1 by R2 into PDR of this. So it will be minus 1 by minus, again it will be minus, so will be 1 by r square, right? It will be simply 1 by r square. At R2, because the actual expression of Ji is this. I have written the final version, so it will be Ji equals to minus DAB DCI dr at R equals to R2. So it will be R2 square. It will be R2 square. Next, we will take the release rate, right? It was release rate. It asked for the spherical release rate, right? Release rate WA will be a flux into the area. So it is a spherical, so it will be multiplied by, so it is, what was JA? It is DAB CA divided by 1 by R1 minus R2 into R square. Sorry. Yes, it is R2 square into, it will be spherical, right? It will be 4 pi R2 square. So this will cancel out. So it will be 4 pi DAB CA by 1 by 1. So now all the values are known. So 4 into pi into DAB is given as, so first we'll calculate 1 by R1 by 1 by R2. So 1 by 1 so it will be 1 by, because it is in millimeter and diffusion coefficient in meter square. You have to check the unit. So 1 by 1 into 10 to the power minus 3 minus 1 by 2 into 10 to the power or 0.002. So it is 500. So now 4 into 3.14 into D effective is 2 into 10 to the power minus 9 into CA1 is 10, okay, divided by 500. So it is coming as 5 into 024 into 10 to the power minus 10 mole per second. Okay, you have to derive the expression for that. A pure spherical drag particle of initial radius r0 dissolves into a large fluid medium where C infinity equals to 0. The solid density of the drag is ρS. Its saturation concentration at the particle surface is Csat, and its diffusivity in the fluid is D effective. Using the pseudo steady state approximation, the time T dissolve required for complete dissolution is given as, calculate the total time for the particle to dissolve completely. So you have to just put the values, nothing else. So T dissolve will be, T dissolve will be, ρS is 5000 mole per meter cube, R0 square is 100 into 10 to the power minus 6 whole square divided by 2, dF is 1 into 10 to the power minus 9 into C saturation is 2. Okay, so it is coming as 5000 into 100 into 10 to the power minus 6 whole square divided by 2 into 10 to the power minus 9 into 2. So it is 12500 second. Okay. So that's for today. So in the middle I have skipped four questions. So if you can solve it by your own, good. And if you cannot solve it by, we will do it maybe in later class or in the final class where we'll be revising all the lectures, right? Okay. So till now, I think you have understood the derivation. You have to do yourself the derivation to understand that how it is. Just by seeing, you cannot remember. You have to do it on your pen and paper. You do it, and this type of equation will come in your exam also. So, and in GATE also, this will help if you solve these things by your own. And I hope this lecture is helpful to you. If you have any question, you can message. Till then, we'll meet on next Tuesday, same time. Till then, goodbye. Thank you.